In this video, we'll be going over geometric proofs. So when we talk about proving things in geometry, we're looking to make a statement and then provide a reason. And the whole reason that we prove things is to consider why these things are working based on other properties or definitions that we know. So when we make a statement, we need to cite a reason why it's true based on given information that we've either been provided in the problem or with our theorems or postulates or definitions that we've studied. So as we continue the year, we'll get more and more definitions and postulates to remember to help us prove things. But for right now, we're going to use the definitions and new theorems that we've learned with parallel lines to start proving in geometry. So in this first part of our notes, we're just going to be connecting statements with reasons to practice them outside of an actual formal proof. So if you were given the information that's here, what statement could you make in a proof and what would be the reason is what we're trying to do here. So in part 1, it says given that M is the midpoint of AB, I'm considering this diagram where M is between A and B, and that would let me know that these two segments would have to be congruent and therefore equal. So a statement that I could write in my proof would be that the segment AM is equal to MB. I could also write that AM is congruent to MB. Either one of those is true because remember this first one is talking about the measures being equal and the one on the right is talking about the segments being congruent. Both of those would be statements I could write, and the reason for that would be using the definition of midpoint. And I'm allowed to use that definition because in the given information, it specifically cited the word midpoint. So I'm relying on that given information along with my knowledge of the definition to make the statement. To the right of that, it says given that the line DE bisects the line AB. So when I hear the word bisect, I know that that means that it's being cut in half. So DE is bisecting AB. That would make these two pieces equal or congruent, like we just talked about, similar to the midpoint, right? So I could make the statement that the measure of AO is equal to the measure of OB, or that the segment AO is congruent to the segment OB. Either way, whichever statement I choose here, I'm going to say that that is based on the definition of a bisector. So I'm using what I know along with the given information to make this claim. In the bottom left, I see given the diagram, and I have a line segment, M and O are at the end, and N is somewhere in between. I don't have any other information. What I can tell, though, is that because N is between M and O, I could make the statement that MN plus NO would equal MO. And remember that that is from our segment addition postulate. So in that postulate, we learned that when a point is in between two endpoints of a segment, that the two parts are going to add to make the entire segment. So I can cite, instead of a definition here, the segment addition postulate. Next up, I have given that the ray OB is bisecting the angle AOC. So again, we have that word bisect, but this time we're talking about angles. Remember that that creates two angles that are congruent to one another. So I can either say that angle AOB is congruent to angle BOC, or I could say that the measure of angle AOB equals the measure of angle BOC. Remember, they're slightly different, just like our segments. If you're talking about the angles being congruent, that means they have the same measure, but when we actually speak of their measure in the number, we're going to set them equal. And this is going to be from our angle addition, or actually not angle addition, excuse me. That's going to be our angle bisector definition. So we can cite that the definition of angle bisector. When you could have done angle addition would be, I also could have just, if I were given this diagram and didn't know that BOB was the bisector, I could have said that the measure of angle AOB plus the measure of angle BOC would equal the measure of angle AOC. So if it hadn't specifically said bisect, I could still make that angle addition postulate claim but this one was a little bit more specific, so definition of angle bisector is what we really wanted there. We're going to keep practicing making these. If you think you're getting the hang of it, you can try them on your own. Otherwise, keep watching. Press play when you're ready to check if you do pause it on your own. So next up, we have given that the angle 1 is congruent to the angle 4. That's all we know. So thinking about what the word congruent means, I can say, well, that would mean that the measure of angle 1 is equal to the measure of angle 4. And this is just based on our definition of what it means to be congruent. So we could cite definition of congruence. In the next example, it says given that AB plus BC equals AC, and we have AB is equal to JK, we have two different pieces of information here. It's telling me that these two pieces are equal to one another. And so that would let me take JK and rewrite it in place of AB. So I'm going to take JK, replace where AB was, and say that JK plus BC should equal AC. The reason for this is just what we call our substitution property of equality. And it's just like if you were to have a substitute at school. Somebody comes in for the teacher and replaces them, and it fills in that same position, right? So the number for JK would replace the number for AB, and it would still be equal. In our next example, it says that angle 1 and angle 2 are a linear pair. So drawing what that looks like, remember we've talked extensively about how two angles that are supplementary and adjacent are a linear pair. So when you have two angles that are a linear pair, then we could say that those two angles are actually supplementary. That's a fact that we would know based on that given information. So I can make that claim that they're supplementary, and that's just based on the definition of a linear pair. And in my final example, I'm given that angle 1 and angle 2 are supplementary. So it's kind of feeding off the one we just did an example of. Well, I know that supplementary angles just have to add to 180 degrees. So what I can write as my statement here is that the measure of angle 1 plus the measure of angle 2 has to equal 180. And the reason for that is, again, just based on the definition of supplementary angles. So I'm going to cite what was given to me with its definition as a way to create that reason. So in part 2, we're going to apply what we just talked about, where we have to give a statement with a reason every time that we're proving something. And we're going to apply this into an entire proof. We call these two-column proofs because on the left you have your statements and on the right you have your reasons. So whenever we're doing any sort of proof with this, we're going to first have a given set of information and then something that we're looking to prove. So I have this given statement that angle 1 and angle 2 are a linear pair and that the measure of angle 1 is 62. So this is just two statements that were already set up for us, and the first reason in every single two-column proof will always be a repeat of that given information. So you're going to write down what was given to you, and the reason is just given. In the next line, we can see that it's already been filled in for us, so we're just looking to plug in the reason this time. So what we want to think about is, well, what came before it that's letting us make this new statement? So I'm claiming that angle 1 and angle 2 are supplementary, and above that I saw that I had that those two angles were a linear pair. So I'm relying on the definition of a linear pair to make the statement that they are supplementary. Looking at my next line, I can now see that the measure of angle 1 plus the measure of angle 2 is equal to 180. So again, thinking about what we just saw, we already claimed that they were supplementary, and then we said that they are adding to 180, so that is relying on our definition of supplementary angles. Moving to the next line, if I notice from line to line, I can see that the only thing that's really slightly different is that I now have 62 in place of measure of angle 1. And if you recall, we had two bits of given information. So we've taken this angle 1 measure and replaced it with 62. So this is an example of our substitution property of equality. And finally, then we're left with the measure of angle 2 equals 118. So to think about how we got there, we would have had to take away 62 from both sides of this equation, and that eliminates the 62 and is left with 118. So that would just be an example of the subtraction property of equality. So think back to when you've started learning about equations, right? Whenever you have something that you're trying to move to a different side, you use that inverse operation. So since I'm trying to eliminate 62 here, I'm going to subtract it on each side. Just an example of our subtraction property of equality. In proof number 2, it is given that C is the midpoint of AB. The segment CD is congruent to the segment DE. We're being asked to prove that the segment AC is also congruent to the segment DE. So over on the right, you can see our 2 columns of the proof here, and we have our given information already stated in there for us, and the given is already listed as well. So down below, I can see that I've now made a new statement that AC is congruent to CB. So let's go back and look at our diagram. If I reread my given info, knowing that C is the midpoint of AB, well, that would make this segment and this segment congruent. And then I was also told that CB is congruent to DE. So all of these can get the same markings here. So in my proof, right, the statement that I make that AC is congruent to CB is really relying on that statement from above. So it's using the definition of a midpoint in order to make that claim. So then in order for us to be able to go to the final line and prove that AC is also congruent to DE, again, I want to think about what's happened so far. I have that the segment CB was congruent to the segment DE in my given, and then I also see that the segment AC should be congruent to the segment CB. We just said that was because of the definition of midpoint. So what that's really showing me is that because they are congruent to the same thing, then they must be congruent to each other. And this is an example of our transitive property. So we're going to fill this in as the transitive property for our final reason. And it's very similar to our law of syllogism that we learned about before. So anytime that something is equal to something else or congruent to something else, we have the transitive property. In proof number 3, we have the given information and the diagram that angle 2 is congruent to angle 3. So one thing that might help you is to mark those as being congruent to each other, either with some highlighting, or you can use their angle symbols there. We're being asked to prove that the measure of angle 3 is equal to the measure of angle 6. So that's not obvious based on this picture right here, but we're going to walk through some of the steps in order to figure that out. So provided that the angle 2 and the angle 3 are congruent, that was our given information. So we're just going to cite the reason there as given. When I look down at the next line, I can see that instead of saying 2 is congruent to 3, I'm now saying angle 2 is congruent to angle 6. So looking back up at my diagram, 2 and 6 are right here. They are angles that are sharing a vertex. They are across from one another on those intersecting lines. And so we can make the claim that they are congruent based on the definition of vertical angles. So remember that when angles share that vertex, they are considered vertical and they must be congruent. So we're using that definition to make that statement. So then looking down at the next line, I can see that the angle 3 is congruent to angle 6. So thinking back to what we said in the example above, we've got angle 2 that is congruent now to 2 separate angles individually. So we can make the claim now using our transitive property that those 2 angles are actually congruent to each other. So the transitive property lets us state that angle 3 is congruent to angle 6. And then it's a very subtle difference there at the end where it's saying where we're proving that the measure of angle 3 is equal to the measure of angle 6. Remember, that's just using our definition of congruence. So we wouldn't want to have stopped at the line above because we had only proved that they were congruent. We're going to cite that the definition of congruence makes those measures equal on that last part. In proof number 4, we're given that line L is parallel to line M. So I'm going to add in the arrows to show that those are parallel for myself. I'm also given that angle 2 is congruent to angle 4, which is not part of the diagram. It's just a separate part of the image there. So it's not on the same set of parallel lines as angle 1, 2, and 3 are, but it's still provided to us. We're asked to prove that angle 4 is congruent to angle 3. So looking down at our 2-column proof, some of it's already filled in for us. The first line is blank for our statement, but its reason is given. We always start with what's there, so I'm going to fill in that line L is parallel to line M, and that angle 2 is congruent to angle 4. Okay. Then looking at my next line, I can see that angle 2 is congruent to angle 3. So in my diagram, I know that these lines are parallel, therefore 2 and 3 must be congruent based on the alternate interior angles theorem. Remember, we learned that when two lines are parallel, any alternate interior angles must be congruent. So therefore, getting to our final line, we've now stated that angle 2 is separately congruent to angle 4 and angle 3. So therefore, our transitive property lets us rearrange that and state that those final two angles are congruent to one another. So angle 4 is congruent to angle 3. We have two more proofs. If you feel like you're getting the hang of it, again, feel free to pause the video and press play when you're ready, or just keep following along. In number 5, it says, given that line A is parallel to line B and line C is parallel to line D. So we have a lot of given information here. This is a huge amount of information to help us make these statements. So I want to mark that they're parallel. Notice we've got all these angles that are marked with numbers to identify them easily in the proof. So it doesn't mean that this measures 1 degree, it's just naming that angle as angle 1, angle 2, angle 6, angle 5, etc. So the first thing that we see is that we have angle 1 and angle 8 listed in the proof, and ultimately we're trying to prove that 1 and 16 are congruent. So if I look on my diagram, 1 is here and 16 is down here. These two angles have nothing to do with each other because I can see that A and B, while they're both on those parallel lines, right, they're on separate transversals. So I can't just automatically say right here that these are congruent by alternate exterior angles theorem because this 16 is on a separate transversal than 1. So that's why we're trying to prove it, right? We're not using one of our theorems here. We're trying to connect it with things that we also know. So considering the first move was that 1 is congruent to 8, right? Those two angles are on the same transversal C, and they are between those parallel lines A and B. So I can state that those are going to be congruent based on the alternate exterior angle theorem because I know that those lines are parallel and that they're sharing that transversal. Looking down to my next row, it's completely blank, and then I see my final row of proving 1 and 16 are congruent. So I need to think about how I'm going to connect those two lines, right? Angle 1 is the same in them, but 8 and 16 are separate. So I want to somehow connect 8 with 16 here in order to connect 1 with 16. So looking back at our diagram, if I focus on 8 and 16, I can see that they are both touching the lines C and D, which we know are parallel, as well as the transversal B. And when you consider them over those two parallel lines with the transversal B, we can see that they are corresponding angles and would therefore be congruent. So I can make the statement that angle 8 is congruent to angle 16 by the corresponding angles theorem. So then that allows us to jump from that final, or to down to that final line, stating that 1 is congruent to 16 because I've now connected 1, 8, and 16 as being congruent. So my final line can be proved using the transitive property. And in our final proof, number 6, we're given that the line A is parallel to line B, just like in the last example, and C is parallel to D, again, just in the last example. This time we're being asked to prove that angle 9 and angle 8 are congruent. So again, looking at those two, as we see them, right, they're not touching the same transversal over the parallel lines C and D. A is with 9 and the line B is with 8. So we can't just automatically go for alternate interior angles here. We need to take a couple steps to get there. So our given information is already listed for us, and then the first statement is that angle 9 is congruent to angle 11. So if I focus on 9 and 11, those two are touching the transversal D across the parallel lines A and B. So knowing that they are corresponding angles over parallel lines, then I can say that they are congruent based on the corresponding angles theorem. The next line is completely blank for us, but if we focus on our final step of trying to prove 9 and 8 being congruent to one another, I can see that I need to make some sort of connection between 8 and 11 in order to make that jump. So if I focus on angle 8 and angle 11 in my diagram, I have angle 11 here with angle 8 here. They're sharing the transversal B across the parallel lines C and D. So therefore I can say that angle 8 is congruent to angle 11 based on the alternate interior angles theorem. And now that I've shown why those two separate statements are true, our transitive property lets us connect them down at the bottom in order to say that our angle 8 is congruent to angle 9 based on the transitive property.